everybody? Can you hear me okay? Great, great. Welcome to Research Week 2024, and welcome to the kickoff event, which is our 2024 D. Wynne Thorne Lecture. I'm Lisa Barreau, Vice President for Research here at Utah State University. And just to give you an overview of Research Week and what's kicking off today, we have several activities planned this week to celebrate the present and future of Utah State's research efforts, including today's lecture, of course. Tomorrow and Wednesday will be the Student Research Symposium here in the library, as well as the Faculty Author Exhibit, which is already happening downstairs and along the south wall, and of course our Student Research Awards celebration on Thursday. So I'm really pleased to kick off the week with this lecture, the annual lecture. One of the things I think that's important to bring up at this point is the momentum that we're seeing in USU research. It was once that hitting the $100 million mark toward the end of the fiscal year meant it was a really strong year. When I walked over here this morning on early April date, we're at $129.4 million as an institution. And so we're looking for a good year again. Maybe not a record year, but it's going to be close, I'm going to tell you. Our record is a little over 160 million. And so when we think about the impact of that research, we can look at various entities across campus. And the Utah Water Research Laboratory is certainly one of those. And so Dr. Tarboton is a prime example of the type of PI to lead USU research as we grow as an institution. So we're glad to see so many of you here today, colleagues, students, friends, and I'd especially like to welcome our prior D. Wynne Thorne Career Research recipients. Looking around, John Neely, are you here? Yes, John, I couldn't see you there hiding. And also Joyce Kincaid. I don't see Joyce in the audience yet. I do, however, see Rose Hugh, who is the 2024 D. Wynne Thorne recipient, and so we'll hear from her next year. Just thank you all for taking the time to be here. A little bit about the award itself. The D. Wynne Thorne Career Research Award is given annually to an individual who has completed outstanding research in their careers and has done the majority of that work here at Utah State. It is the most prestigious research award given by the university. Award recipients are invited to give a lecture at Research Week the year following when they are recognized. On that note, today's lecture is to be presented by the 2023 recipient of the award, David Tarboton, the director of the Utah Water Research Laboratory. I'd like to welcome his dean, Jagath, to come to the podium to introduce Dr. Tarboton.
Thank you, Lisa. Good morning, everyone. Thank you for coming, and it's my great pleasure to introduce Dr. David Tarboton, Director of the Utah Water Research Lab, at the same time Professor of Civil and Environmental Engineering. I've known David for a long time, probably over 30 years. I think we came to USU almost at the same time, and Runa was the department head at that time. So anyway, with that short introduction, I have some prepared statements about David's accomplishments over the years, many years here. In his 3 decades at Utah State University, Dr. Tarboton has produced exemplary and impactful research. His work in hydrology and information system led to the development of HydroShare, a system that allows researchers and others to share hydrologic data and models. The platform fosters collaboration and further research goals by making the data more accessible for researchers around the world. Dr. David Tarboton earned his Doctor of Science degree in Civil Engineering from MIT and began researching at Utah State University soon after. He has been heavily involved in research since arriving at USU, serving as chairman or director of various initiatives and task forces. In 2019, he was appointed director of the Utah Water Research Laboratory. As you know, the Water Lab has a nationwide, actually a global reputation in water resources engineering and environmental quality research. Over the years, David Tarboton has received numerous recognition for his work, including a 2015 Robbins Award for as Faculty Researcher of the Year, a 2018 Fellowship recognition from the American Geophysical Union, and a 2020 David R. Maidman Award for exemplary contributions to water resources, data and information systems from the American Water Resources Association. Plus, of course, the 2023 Wynne Thorne Career Research Award. Thank you, David, for all your hard work at Utah State University and for the College of Engineering. Please join me in welcoming Dr. David Tarboton.
Well, thank you. I'm honored and humbled to have received this award. Thank you to all who've helped me along the way. My wife, Debbie, it's a special occasion. She's actually come to this event. It's very difficult to get her to come to university events.
I agree.
So my family, my students, my colleagues, USU and the Water Lab for recognizing this. I arrived in Logan in 1990. It was actually Bill Grenny was department head, so maybe there was a rapid transition there when Lauren Anderson took over. Jagath was about the same time. Debbie and a newborn baby, Bronwyn. I think I had any energy and drive, a bit of a sense for research, but nowhere near an inkling of what was really going to go on. And now, 34 years later, I find myself having spent more of my life here than anywhere else, which I guess is quite interesting. Debbie followed me around the world. She's sacrificed a lot, gave up her career as a librarian to raise the children, Bronwyn and then Paisley that came a little bit later. I think she actually found her true calling being athletically talented as a ski instructor, now ski school director at Beaver Mountain. She's taught Art a little bit about that, maybe. And she's very good at that. Now those two children we raised have both grown up, left home. Bronwyn is living in New York, pursuing her own dream in musical theater on Broadway, and Paisley is in Salt Lake City, about to move to MIT. So hopefully there'll be a closing of the circle there, doing an MBA. So that's a little bit different from engineering, but it's an engineering MBA. So that gives you a bit of an idea for who I am. But this award is for research, so I better say something about that. And I guess we've got the title here, Let the Data Speak. Looking back, if I think about what might have been a theme with what I've done, Let the Data Speak seems to bring things together. It's a bit of a vision and an ideal and maybe an approach. I have by far not always done this, so some of this message will be do as I say, but not necessarily as I've always done. Data and the best science to make decisions. Wouldn't it be wonderful if we always followed that? This involves transparent, open, reproducible research to engender trust in the research findings. It involves data being findable, accessible, interoperable, and reusable, or the so-called FAIR principles. Drawing on those and working with data, I've learned that the way that data is organized can enhance or inhibit the analyses that can be done. I'll be getting into that a little bit. I've learned that collaboration is needed to generate understanding, and describing data precisely is important for collaboration, so the other disciplines can actually understand what's going on. And I I see Courtney in the back there, and she works in social sciences but tries to work with hydrology data, and it's always important trying to describe that. And I note also that if you look at the research web page on Wynne Thorne, he was an advocate for interdisciplinary research. So this also conveniently aligns well with my role now as director of the Water Lab, where the mission is to conduct collaborative research throughout the state, the country, and the world, advancing innovative solutions, promote scientifically informed policy and management decisions, and train tomorrow's leaders. So I think I'm hoping to try and bring, or I hope that I do bring some looking at the data elements to leadership in the Water Lab. And I'm proud to be working with the people at the Water Lab, some of whom are sitting in the back here. So this is an outline. I'm going to present my work grouped into 4 themes. Each represents a slightly different take on the sort of overall let the data speak, and then I'll end with some closing thoughts. And I hope it doesn't get too technical, but I'll be happy to go into depth with anybody afterwards. So the first is hydrologic information systems. So Jagat mentioned that. This is one area where I think we've made a difference. We've worked quite closely with COHASI, that's the Consortium of Universities for the Advancement of Hydrologic Science Incorporated, and hopefully that's the only time I will say that mouthful of a name in this talk. But when I'm saying COHASI, it's that organization of hydrology research universities around the country that has been the organization that's been a home for a lot of our work. We worked on the development of the first quasi-hydrologic information system, and then later HydroShare, and I'll go into a bit of detail of these. But first I want to motivate the need for formalized information and data management systems. So I also mentioned collaboration a bit earlier, and if you are collaborating, somebody may say, can I please use your data? Maybe what you get is something like this. Some numbers randomly arranged in a column. What on earth do they mean? So that's why we need metadata, especially when we're going to describe it and share it with other people. So I'm going to go through a little bit about how metadata is structured to describe data, and this is an example. Perhaps the data represents stream flow from a watershed. So there's a watershed that actually is Dry Canyon, just out the window there. There's not often stream flow there, but let's think about perhaps there being stream flow there. Maybe you've got some observations. Rather than just the random numbers from the previous screen, now we've got data values 43 cubic feet per second. So we're saying what the units are. We're saying what the variable is that's being measured. It's stream flow. We're saying the date and time that it's being measured. We are saying where it's measured. So we have a sampling feature. The specific sampling feature in this case might be a stream gauge that then relates to the feature of interest, the thing that the measurement applies to. In this case, the measurement could apply to the watershed represented as a polygon, a geographic polygon. So now these are some of the things that we have to think about as we are describing our data carefully so that it can enhance analysis, or it could apply to the stream where if you're interested in the flow in that particular stream. So this emphasizes the point that I wanted to make. The way that information is organized can enhance or inhibit the analysis that can be done. And what I illustrated with those diagrams is a data model, the structure that defines the way data together with its metadata is organized to support analyses. And it was fairly late in my career. I'd probably been at USU maybe 10, 15 years before I first heard the term data model, which initially thinks of it as a contradiction. You've got a model, which is a representation of processes, and you've got data. So what's combining them together into one concept? Putting it another way, it is as important to represent hydrologic information precisely with data as it is to represent hydrologic processes with equations. That was a thought that came from David Maidment, who is pictured there, and with whom I forged a collaboration really early in my career and collaborated closely initially on the quasi-hydrologic information system. We actually taught a GIS and water resources class together, with him in the classroom in Texas, me in the classroom at Utah State. Initially it was asynchronous, but then at the end we had two-way video going back and forth. So there was a really strong and rich relationship with him there. And he made the point that we might think of process science, description of physical processes with equations, which is the way often people think about science. We discover how the world works. We maybe represent it by an equation, maybe a famous equation, E equals mc squared, or in hydrology, Q equals CIA, which is the rational equation for calculating stream flow based on rainfall. But he made the point that the way we describe the environment with data is just as important as the way we describe processes with equations. And we need to have the hydrologic environment, the hydrologic conditions, and the physical laws and principles involved. So the quasi-hydrologic information system was set up to formalize the sharing of hydrologic data using web services, and this was the first information system project that I worked on. I'm not going to go into a lot of detail on that, but it was really a server-based system where data was shared using web services. Jeff Horsburgh did his PhD on that topic. So he was another real close colleague that I worked with, and it's really gratifying to see that for his work started off looking at watershed information systems for the Bear River, moved into his PhD. Now he's on the faculty, and just on Friday got promoted to full professor here. So thanks, Jeff, for all your hard work, and well done. And the image at the back is blurred out because I didn't want to see the details, but you might be able to see just the colors slightly. That is the database schema for the observations data model that we developed to organize hydrologic observations into a relational database. That was version 1. There was now version 2 that Jeff had a paper about, and there's still ongoing work on those systems. It was actually quite hard for individual researchers to share data with the quasi-hydrologic information system because it was essentially limited to time series of discrete observations and required a server. So that led us to conceive HydroShare, which was intended to be a much simpler system where users could just upload their data, perhaps a bit like YouTube, the way you would upload videos. You'd use HydroShare to upload data, Facebook to upload pictures. We were starting it at the time that the sort of social media was just booming, and it was an online collaboration environment for sharing data and models. We had funding from the National Science Foundation for that, and I quickly learned when I was presenting ideas on this that when proposing to the National Science Foundation, you need to lead with a question or a challenge, a grand challenge they like to call it. So we used a few grand challenges here. How to better forecast, plan for, and mitigate the effects of floods. That's 6th West and Logan during some floods, I think it was 2012-ish, although, yeah, done. So we do actually get floods in Logan that interrupt our transportation infrastructure. How to ensure sufficient water resources in times of drought. So that's Lake Mead, Hoover Dam, and you can go there and see the sort of bathtub rings. The water levels are critically low. And then a photograph that I didn't take, but how to provide access to clean water. This is a water treatment plant. So as we think about the important challenges that water researchers face, HydroShare was built motivated by those, but really the idea that advancing understanding and generating knowledge depends on collaboration and data sharing, which demands open data. It demands integration of information from multiple sources. We've gone beyond the point where somebody can perhaps measure one thing and make a new discovery. It requires easy to use and generally accessible shareable computing so that the computer models that one person is using can be used by somebody else. And it requires working as a team and community. So I like to think of water research as a team sport. And what better picture to show than that? So that's my wife Debbie playing the team sport of hockey. So let me tell you a bit about HydroShare. It's a system for sharing files with Dropbox or Box-like functionality. And many of you probably share files in Box, and maybe the files you received in Box have names and says version 1, version 2, use this final version. And it's hard to know actually what's in them. So often for formal data sharing and publishing, we need to do better. So in HydroShare, we try to addition to just sharing the content, also bring with it metadata descriptions, address machine readability through application programming interfaces, use web applications, social functions so people can comment on the information, and use digital object identifiers to make the information citable. So a goal, and so there was value-added functionality there. So the goal of HydroShare was to advance hydrologic science by enabling the community to easily share the research products resulting from their research, but not only the papers, also the data that goes with the papers. So that's been one of the things we've been pushing. When you publish a paper, and it's often now required by journals to say in the sort of open science part of the paper where the data is so that it can be reproduced to enhance trust. HydroShare was developed working with a large team. This is the group pictured at the Renaissance Computing Institute, or RENCI, that served as our technology partner. We also met a few other places. This was at Shepherdstown, the National Conservation Training Center. So it was really gratifying and challenging to work with a large number of people. So the work has been quite impactful because it came about at perhaps the right time, or maybe it was motivated because the whole making data findable, accessible, interoperable, reusable was sort of hitting the mainstream, and HydroShare served the need for the hydrology community. This slide comes from the American Geophysical Union a couple of years ago when they were sort of pushing that idea. So what are the take-homes from this section? Data and models are first-class products of research. So rather than only thinking of data as perhaps supporting a paper, it's something that's worthy in its own right and should be shared. Research data management needs to start at the beginning of a project. Resources should be created and systematically managed through the full research life cycle. And I talked about resource there rather than data because we sort of adopted a jargon in HydroShare that we would use a resource to describe everything because it includes models, computer code, other things as well. Another important thing was to rely on and use standards. If you can share your information in a standard format, the chance of other people being able to work with it is a whole lot better. And a user community is really important. I think HydroShare has persisted because it's now been adopted by Quasi, and I'm no longer running it. Quasi's running it. And there were other systems built more or less at the same time that didn't have that sort of built-in community and have, even though they may in some cases have been better technologically, have gone away. Switching gears, I was hoping I could see how am I going on time?
It's okay.
Nobody worries about that. Okay. Usually you can see on PowerPoint here how long you've been going from when it started, but this one was set up, it says 86 minutes, and I know I haven't been going that. So the next part of this work, I'm going to be talking about non-parametric stochastic hydrology, or thinking about streamflow data. This is a topic that I got involved with earlier on in my career, and stochastic hydrology is really the field where we look to produce streamflow for managing systems like the dams in the Colorado, recognizing that the future is not going to be the same as what's happened in the past, but it's perhaps statistically similar. So stochastic hydrology uses statistics to produce streamflow sequences with which to test the operation of systems. When I first showed up here at Utah State, Doug James was the director of the water lab, and he invited me to participate in a severe sustained drought project, and that got me involved in this area, and it also got me connected to some of the community working on the Colorado River system. The other person pictured there is Manu Lal, who was here at the time, became a real close colleague and friend, and he introduced me to the whole idea of non-parametric statistics, which are statistics where we avoid the assumptions of, say, for example, assuming a normal distribution or assuming linear correlation, and instead you just resample directly from the data to represent hydrologic processes. So here's a technical slide that illustrates that. But this is annual streamflow data from, doesn't matter too much where the stream is, it happens to be the San Juan River. And the histogram sort of shows the distribution. If you try and estimate the probability distribution for that, you see that it's got two modes. There's two different peaks to that. Whereas if you try and fit a normal distribution, that doesn't capture that sort of variability. So if you want to be able to simulate what actually happens, you may want to represent that by modality. So that's part of the structure that we try and capture with these simulation models that that produce streamflow ensembles to use in water resources planning. Here pictured are two of the students who worked on that. Ashish Sharma was one of my first PhD students. He's now moved on to University of New South Wales in Australia. And Balaji Jakapalan, I was on his committee. He was Manu's student, and he's now at University of Colorado. This work is actually going on today. So we've sort of come full circle from in 1990 through about 95, working on severe sustained drought. Fast forward many years, for the period from 2000 to about now in the Colorado has been a severe sustained drought, known as the Millennium Drought. And working with Jack Schmidt and another student of mine, we've looked at all of the data. So that rather busy and complicated looking plot is the averages over different durations of stream flow in the Colorado. So from that you can see how severe a drought may be, if it's got a duration of 1 year, 2 years, 3 years, and so on. And then we can have models that simulate that. So this is work with Jack Schmidt, who I'm sure many of you know has been heavily involved in Colorado River work here at Utah State. and my PhD student Homa Salahabadi, who will be defending her dissertation just as soon as we can get it scheduled. She gave it to a committee just last week. So the take home from this part is that droughts that have happened in the past may happen again, so we need to plan for that. We also need to have adjustments to account for non-stationarity and climate change. So switching gears again, terrain analysis using digital elevation models, or I think of this as letting the topography data speak, or TOWDEM is the acronym. This has been a big part of my career. It grew from early work with my PhD when I started working with digital elevation models to now where we've got software that's a plug-in to ArcGIS that is quite widely used, and some of the methods have been built into the ArcGIS core products. So let me talk you a little bit about through this slide. A digital elevation model is topography data, but it's a really simple data structure. So if you look at the sort of carpet here, you can imagine, well, you can see these little squares of carpet. You can think of an elevation value associated with each one of them. So there's a number in each square. From those numbers, you can figure out how steep the slope is, where the water will flow. It will flow downstream from this carpet square to the adjacent one based on those elevation values. So calculating those flow directions is the first thing that one does. One also has to worry about if some of the cells are lower than all the surrounding ones, that's water that would not drain, and those cells need to get filled up. So you have the model of each grid cell flows to one of the grid cells that, you think of it as a set of arrows. This set of arrows here, that's the flow direction grid. From that, you can then count how many grid cells flow through any one grid cell, and that gives you an idea of the watershed being the area that drains through any particular point, and that's sort of depicted on the top right. You can then perhaps apply a threshold to the counting of the number of cells that drain through each cell and map streams. You can say if some stuff, maybe that stuff is sediment or contaminant or water, is flowing along the direction of the arrows, this is where it goes. So you end up with a rich set of information about how water and other substances move over the topography, starting from this fairly simple gridded data structure. So that was all built into software. I also found that the way things were traditionally done seemed to be limiting. There was a model that had stuff start in a particular grid cell and move to one cell downstream, but that could therefore then perhaps not follow the topography directly, and it was better to have the flow perhaps be shared between two downslope grid cells, perhaps follow a path that is truer to the topography, although then it spreads out. So we went from 8 possible directions from this cell to the 8 neighboring cells around it to an infinite number of directions. So we took the 8 on its side, called it D-infinity. It was a cute name. It caught on, put the software out there for people to download and freely use. So this is the sort of information you can get out of that. So if you apply that method over topography where there's details on roads and perhaps even hiking trails, you can see how the water flow paths get deflected. You can see in a rich set of detail how water moves over the topography. So that led to a number of other applications. One of them was with terrain stability mapping. Bob Pack at the time was in British Columbia working in geotechnical consulting, and he was interested in landslides. He called me up and said, can we use your approach of calculating flow directions and calculating contributing area to map landslides? We ended up working on a model for that was called SINMAP, a stability index approach to terrain stability mapping. And it was able to model where things like landslides may originate from forest roads. Kiran Chinaya-Kanhali was a student who worked on the uncertainty associated with some of the parameters of that model. And that took me up to Canada, where I put this slide in because it shows just some of the contrasts and contradictions that we see. Norris Creek Integrated Watershed. You're entering a community water supply. Any harm to the environment may affect water quality. So you expect this to be somewhat of a pristine place. This is an active logging area. Logging traffic has right of way. And we had to keep out of the way of there were really huge logging trucks. Well, it's actually two trucks with a huge log in between, and the sort of front driver and the back driver have to keep themselves coordinated. Use the roads at the owners, so not exactly pristine. Please report any acts of vandalism. Your cooperation is appreciated. And there's bullet holes all through the side. So in Canada, they have the Wild West too. All of the time we were working with digital elevation models, the data was getting better. Coarse resolution information that we had available in the 1980s went down to fine resolution data that was available in the 2010s. That fine resolution data meant the computer files were bigger and bigger and bigger. The software that we had, computers were getting faster, but they were not really keeping up. So we had the challenge of increasing digital elevation model resolution that demanded a parallelization approach. One day, I got a call from Rob Wallace. He's a program officer with the Army Corps of Engineers. And he said, we like your software. We would like to use it. We wanted to work over bigger data sets. Can you develop a parallel version for it? Well, I didn't know anything about parallel programming, but when a program officer calls you, you don't say no. So we said yes. He says, well, just send me a proposal. Don't make it too long. So we knew that that was going to get funded. And I went, and Kim Schroeders was working with me at the time. She knew Dan Watson, who was a professor in computer science. We got connected. Ahmed Yildirim was a PhD student who was also in computer science, and we developed a parallel version of the software. We also enlisted the help of the National Science Foundation Exceed system that Yan Liu was working on. He provided consulting work for us on that. So we developed a parallel version of TAUDEM that was able to work much more quickly over much larger areas. I was also teaching the class with David Maidment. I mentioned him just a bit earlier. And he came to me and said, can your software calculate the height above the nearest stream? Because he was interested in modeling across the continent as part of the sort of national water model that he was conceiving, the potential for flood and inundation. He had this idea in mind. Flooding occurs when the water depth gets greater than the height that you are above the nearest drainage. Height above nearest drainage beforehand became the sort of acronym, and he wanted to evaluate that quantity. And my response, well, he was initially asking me, what would it take for you to develop a method to do this? My answer was, well, it's actually already buried in the software, because we had thinking generally been calculating the distance from any point to the stream. And when we were calculating distance, I thought, well, let's do it generally. We could calculate distance horizontally, we could calculate it vertically, we could go uphill and downhill, you could even go along the slope. But one of those quantities you could just specify with a particular option in the program. Vertical distance to the stream gave David Maidment exactly what he wanted in height above nearest drainage. The student who worked on that was Teklu Tesfa, who's now at Pacific Northwest Lab in Richland, Washington. And he did his work on soil depth in addition to this hydrologic proximity work. So there he's seen measuring the depth of soils. It turned out that working with hand took off. It became pivotal to the National Water Model-based flood inundation mapping, and Yan Liu put together this first continental scale map of height above nearest drainage, taking the software and applying it applying it using supercomputers to apply it over the continental US. So there's Yan Liu again, and my PhD student Irene Garusi-Najad worked on actually applying it and testing it in the reach of the Bear River below Tremonton. You might remember that a few years ago when we had the sort of January, February rains, there were some floods there that she tried to model. So the take home from this work is that starting from a simple grid digital elevation model, pretty basic data structure, you end up with a rich set of data structures and information useful for hydrologic analysis. And that software that's shared in a way that's simple and accessible has an impact and can make a difference in some of these things. So I've also worked in hydrologic modeling. So here you can think of this as letting the data speak through models. One of the things when I first arrived at Utah State, we arrived in January, there was snow outside, and I needed to do something that was relevant locally, so started work that eventually became the Utah Energy Balance snowmelt model, trying to keep track of all of the energy fluxes involved with sunlight going through vegetation, the sunlight impacting, reflecting from the snow, the energy content, how much water is in the snow, the interactions with the ground below. If anybody wants to know the details, I can go into that, but we're probably getting to where people are getting worn out with slides here. Hopefully this is not death by PowerPoint. But these are some of the people that worked on the snowmelt model. Tanry did his master's, and he was the first person. Charlie Luce, I ended up doing a lot of work with him, and now he's in Boise with the Forest Service. Jincheng Yu brought in the components of the model that looked at how a freezing front can penetrate down when it gets cold on the surface. Kevin Williams and Rajiv looked at the sort of spatial distribution, and Vinod looked at the vegetation components. One of the things that I learned in working with the snowmelt model is that sometimes the field details are important. So when we first put together the model, and here we've got a graph that represents over time the snow water equivalent, and the blue squares are the actual observations. When we first put together the model, we got this data, it came from the Central Sierra Snow Lab in California, and our model was this sort of dashed line. And we thought, oh, well, this is doing reasonably well. It's not too different from the observations. I mean, after all, it's a model. No model's perfect. And we were happy with that. Went along for a couple of years later, we were trying to look at how much water was lost due to sublimation, which is the vaporization of water from snow. This field site is actually out near to Campbell Scientific in the valley. It's no longer there. It used to be Rick Allen's lysimeters. We started actually measuring the temperatures in the snow. And we found when we measured the temperatures that told us something about the energy content, it was very different from what we were observing. And that said, oh, here we've got something wrong. Our processes aren't quite right. We developed a new approach to fix those processes, and lo and behold, when we went back and ran the model here, it followed the data just so much more closely. So that gave me some belief that the stuff, physics you learn in class, is real, it works. Talking of details, when you look closely at snow with an electron microscope, you see what you may know, that snow is made up of beautiful crystal structures. It's really quite a wonderful substance. Doesn't look so nice in our equations. So I thought I'd put up this Kelvin cartoon. Today for show and tell, I brought you a tiny marvel of nature, a single snowflake. We can learn a lesson from it. When you bring it inside, this exquisite molecule becomes a boring molecule of water, just like every other. So now while the analogy sinks in, maybe we should go and have a look outside. Or maybe we should really go have a look outside. Because
It's 12:30.
who wants to take a peek? I'm going to see if there's an eclipse going on. Can't see the sun from here. Bad planning. But let's wrap this up to give me a chance to actually maybe see what's. Yeah, I've got eclipse glasses all over the place. I don't think I have enough for everybody. Where did my clicker go? The research office is going to have to find another clicker because I've got the second one here. So one of the areas that I've worked on is distributed hydrologic modeling. So this shows quite a bit of detail over a watershed where one can take detailed representations of the hydrologic processes, apply them to each single watershed, perhaps delineated using the terrain analysis software, and then add up the flows to get the flows at different rivers. This was a watershed in northwest Washington state known as the Nooksack watershed, so that we had a large project involving a number of people. I think Dave Stevens might be the only one from that. Anybody else from the Nooksack project? You worked on the Nooksack project, did you?
Yeah.
So what was interesting about this is beyond just the hydrologic model, we added water management, added irrigation, added withdrawals, water flowing back into the streams, and that I think has ideas that could be applied elsewhere. So here are some of the people who worked on the Nooksack, led by Tom Hardy. Mac McKee was involved, Beth Nielsen, Christina Bandaragota, a PhD student. She ended up working on it more than perhaps she bargained, because she got a job in the state of Washington and continued as a consultant. David Stevens and Ross Woods helped us out from New Zealand. Would be remiss if I didn't mention anything about the Great Salt Lake. I'm not going to go into a lot of detail, but we all know the Great Salt Lake is at critically low levels. It was fortuitous that when the low levels started when it started really getting attention a couple of years ago, I had a student, Ibrahim Mohammed, work on this 12 years ago, effectively looking to understand how changes to the inputs would affect lake levels. So we were able to rely on his work in the strike team to try and help inform the amount of water that's needed to restore the lake back to healthier levels. And there's a picture of the lake that you can see with the railway causeway going across. It's a really interesting system because it's divided and there's a different salinity on either side of this. Another question that comes up in modeling is, how does stream flow respond to forest disturbance? This also raised its head in the Great Salt Lake because we had politicians suggesting to clear the trees that consume water through evapotranspiration and get more water to the lake. Sarah Goking had just a couple of years previously done her PhD focusing on this topic, again bringing different data sets together. She works for the Forest Service, the Forest Inventory Analysis Group. She was given time off to come and do her PhD, put together a large data set on forest disturbance that she had with hydrology data, and looked at things like mortality and how that results in changes in stream flow, and found that for arid watersheds, mortality can actually result in decreases in stream flow rather than increases, because you get the regrowing vegetation can consume more water. So the whole story about how forests impact stream flow is a lot more complicated. And while there may be good reasons to manage our forests to prevent fires, for example, you shouldn't count on it as a source of additional water. So there's a picture of Sarah. So, so in terms of models, the take home is that advancing capability for hydrologic prediction needs to take advantage of new information and process understanding, using new technology to inform better decisions. So that's all that I've wanted to say about research. It's probably enough. I wanted to, just before closing, mention the water initiative. This was something that was started by Kermit Hall when he was president just over 20 years ago. I had just become a full professor and I was asked to chair the Water Initiative Task Force. And it was asked to look at ways to strengthen USU's water programs. And we looked at the sort of biological sciences, physical sciences, social sciences, and looked at the different units across Utah State and saw where they fit in, and wrote this report, which I think the only place you can find it now is actually on my website. The university archives didn't manage to keep track of it. So somebody can prove me wrong on that. But the idea was really that there's a strong need for interdisciplinary collaboration. Together we can make a difference. There we were presenting the final report to the president. This led to the starting of the Spring Runoff Conference. It also led to some seed work in hydrologic information systems and experimental watersheds that, at least in part, contributed to things like the Logan River Observatory, as well as the more recent work on hydrologic information systems. So, reflecting a bit on what matters. The people. It's the people that have carried the work on. I sort of mentioned the students who are now working with the ideas developed in other parts of the country and the world. I've also thought about what makes some things persist while others do not. Many of the things I mentioned today are parts of my work that have actually persisted, but there have been projects that you write a paper and nobody cites it, it's gone. Taudim and HydroShare are perhaps two things that have stuck. And I think Taudim stuck because the software ended up being easy to distribute, plugged into a well-used ArcGIS system, and met a need. HydroShare has stuck because it's now being picked up by Quasi. It was really developed for Quasi, and it's serving that community. Other systems without that have gone by the wayside. I also like to think about sort of research data management. I think some of the ideas that we've advanced a little bit with systems like HydroShare, things like data being first-class objects and how to put the metadata together and how to make it easy for users to add the metadata and, where possible, for it to happen automatically, are messages that we could perhaps apply in other research data management systems. Integration. A lot of good knowledge comes by combining information from multiple sources. So that's an important thought to bear in mind. And collaboration, because it's people in different disciplines coming together. So to wrap it up, thanks again to students and colleagues. There wasn't time to mention everybody. Thanks to the prior awardees and the committee for recognizing my work. I guess Chuck was also a former Wynne Thorne winner. You didn't get to give your lecture, you told me the other day, because of COVID, so that was sad. a few of the others I've connected with as well. Thanks to my family, most especially Debbie, who's sacrificed a lot, followed me around the country and the world. And it's a challenge for anybody to tell us, except Debbie, where that picture is. Some of you may recognize it. It's a relatively famous place. And thank you for your attention.